Recorded is rolling. It is Monday, October 3rd. I know I haven't seen you guys in a few days. So last Tuesday was the last day to tell you guys because well, had a few days off because of the hurricane. But here's what we're doing. Today and tomorrow, we're gonna finish up this section, which is dynamic forces, Newton's law of motion, right? Push on some net force causes acceleration, that sort of thing. Right. So today and tomorrow, we're gonna wrap up some things. Right. And then starting Wednesday, we're starting with the next session. So that's like big picture point of view what we're doing. Right. I know that I had some things that were due, like, well, I posted due dates that were hurricane days. So here's what we do about that. Those textbook puzzles, right? All those textbook puzzles, you guys remember those? I'm gonna pick those up from you guys just sometime this week. Get those into me. If you're finished with them already, some of you guys already put them in the grade tray. That's awesome. All right, and then pretty soon here, probably tomorrow. I'm thinking I'm gonna get you guys your next open notes take home quiz and give you guys a few days to do that, and that'll be due on Friday. Okay. All right. So today we're just gonna focus on the friction lab, and then tomorrow I'll get you guys for your next open notes take home quiz, and then that'll be due on Friday. Okay. All right. You guys good so far? Everybody right? All right. So what's the deal with this friction lab? So you guys have this page in front of you? Okay. All right. So this friction lab is going to be in two parts. Right. It's going to be a part one, part two. Okay. Now part one here, I'll model this for you guys. I split this paper in half. Right, one for each half. Okay. Part one's going to be pretty straightforward. All you need is some lab weights. You guys have a box of lab weights at your desk and a spring scale. You guys got those items? Okay. You might have a brown spring scale, which is pretty good for hanging weights, and you might have a blue spring scale, which has a very small spring constant. It's better for like pulling the weights. There are some spring scales on the lab tables back there. Some of my earlier classes, they pulled some of the materials back to the lab table to short some materials. Okay. So what I'm gonna do here is suppose I pick this up. Can I grab the weight by doing this? The weight? Okay. Now, guys, there's two readings on this. There's grams on one side, and turn this over, it says newtons on the other side. Which one of those units determines weight? Newtons. You guys measure in force in newtons, right? Okay. Hanging force, pulling force, right? Forces in newtons. Okay. Now, what if I do this? What if I drag this across this paper with a horizontal force? Right. Notice I'm pulling at constant velocity. Guys, if I'm pulling at constant velocity, what is the net force? Zero, right? Because it's not accelerating, right? And I'm pulling with a force, but there's also a what force keeping that in check? Friction. This is going to be a friction lab. You guys see where it's starting to come together? Let's do a free body diagram on what I just did. FBD, free body diagram. You guys remember this? No, good. No, it's back a few days here. All right. So there's the lab weight. There's the center mass. Right. Now, as I was pulling across at constant velocity, I should switch color here. Yeah, let's bring up the paint. What was one force on that lab weight? Gravity. Yeah, it's one weight, gravitational force. So I'll call it mg, right? Mass times gravitational field. Right. Maybe for example, like 5 newtons. Is this about a 5 Newton weight right here? 5 newtons? I think so. Okay. Here. What force was keeping that in check? The normal force. You guys remember that? F sub n, normal force, right? Which, as long as you were pulling strictly horizontally, then the normal force should balance out with weight, right? They're equal in magnitude. Is that true? Okay. Speaking of pulling, that's another force I've put on here, right? The applied force, the pulling force, the spring force. I'll call it F sub pull. That's the force from the spring, right? Right. Now, if I stopped right there and walked away from the paper, is that the complete picture? I'm missing something. What am I missing? Friction force. And should the friction force be exactly the same magnitude as the pulling force? Yeah, because that would put it in equilibrium, which means zero acceleration, right? Which means constant velocity. That could be constant velocity right there, couldn't it? Could be. Right. Now, also going back about a week ago, I should tell you guys, here's the perfect time to tell you guys the purpose of this lab. Right. The question you're trying to answer is, what is the coefficient of friction between two material surfaces? What's the coefficient of friction? Okay. Now, this is a material property. So if you are really scientifically strict about it, then you'll keep the materials the same. That's why I wrapped this one up in paper, so you can do paper across paper, right? Because you guys know some of these lab weights are like bare metal, some of them are covered in paint, right? And then you have surface, you could choose different surfaces. You guys got a desk surface, maybe there's a textbook, maybe you have a like a lab paper notebook, or who knows. But if you really want to be scientific about it, you have to control for the lab surfaces, right? The two surfaces, they're rubbing against each other. Okay. And then once you have that, you guys remember the coefficient of friction. I'm going to go a step more granular. I'm going to say coefficient of kinetic friction. If the two surfaces are actually sliding past each other, is the ratio of two of those four forces. Which two forces? It's what over what? So yeah, the friction force compared to the normal force, right? I mean, if it's coefficient of friction, I have to care something about the friction force. So that's your numerator, right? And then the normal force, right? So there you go. There's coefficient of friction. That's your lab goal. Do you guys think you could do that? Do you guys think you can read the pulling force and say, well, that must be equivalent to the friction right there, and then hang it, say, okay, that's the weight. Well, that must also be the normal force. As long as I pull strictly horizontally, that doesn't throw this guy out of whack. So that guy is that guy. Goes right there. You guys could do that. Okay, that's pretty much the first half of your lab. Okay, right. So weight, pulling force, take the ratio of the two. Graph. Ooh, I bet you guys can figure this graph out. Y versus X. Right, answer these questions. You guys think you do that? All right, who's got a question so far? You guys all right? All right, let's switch over and look at the second half of the lab. I'll get you guys set up on this. Okay. So the second half of the lab is answering the same question. What is the coefficient of friction? Okay, coefficient of kinetic friction. Here, let me write this out. What is the coefficient of kinetic friction between the two surfaces? Between the two surfaces. Okay. But the second part involves a different procedure and a different thought process. It involves taking your desk or whatever surface you're using and tilting it up to some angle. Right? You guys remember that poster hanging above the door right there? Look at pull through by diagram. You think that's kind of where this is going? Okay. All right, so here's your lab weight parked on that desk. Tilt up at some angle. Okay. Now, do you guys think? Suppose this. Is sliding down at constant velocity? Because sliding down at constant velocity could answer this question too, right? Coefficient of kinetic friction. Right. Sliding down at constant velocity. Now, if that's true, do you think that if you knew what this angle was for that condition, that would be enough information by itself to figure out what is the coefficient of friction? Right? Like there's gonna be some coefficient of friction that aligns with some angle. Like if you replace the surface with sandpaper, do you think you have to tilt this up at a steeper angle to get slide down constant velocity? Ooh, I think so, right? If you knew one, you could probably figure out the other, right? So let's do the next step. Let's get some force vectors. I know this guy has a weight, mg, just like before. It's the same weight, right? I should introduce a Cartesian system that runs perpendicular to the surface and parallel to the surface, right? We've done this a number of times in this one, right? And this weight I'm going to re-represent in terms of that rotated Cartesian plane, because that weight is partially pushing into the incline and it's partially pulling parallel to the incline. That way. Is that true? Okay. That angle theta is the single theta, it's the same theta, same angle, which means this guy is mg sine theta. This guy is mg cosine theta. Right. What force is holding that block up, sort of? Normal force. All right, normal force. Right. You guys see where this is eventually going to be going? That has to balance with that one. Okay. And if I stop there and walk away from the paper, is that the complete story? Yeah. This might be the complete story, or pretty close to it, for your Hot Wheels cars rolling down the incline, but those were accelerating. This one, right? You guys remember that? One of the very first labs you guys did. Okay. But this one, if you want to slide down at constant velocity, it must be kept in check by a friction force, but F sub FR, force due to friction. Okay. that's exactly balancing out the sine component of the weight. Is that true? Okay. Now, I've got some more steps that I want to do to finish this off, but I think that's a good pause point right there. And I want to see if you guys can kind of figure out where this is going. Okay. So I'm saying measure, okay, so different weights could be a 5 Newton weight, for example, could be this guy might be 5 Newtons. Okay. Choose some different weights. See what is the angle that it breaks friction? Okay. Ooh, what's this? What's the deal with this? Tangent of the angle? See if you guys can figure that out. And then the last about 10 minutes of class will go over the answer. Can you guys graph tan theta versus weight and then figure out the answer to these questions down here? All right, so I'm gonna pause this recording here. I'll leave this up for reference in case that helps. You guys have a lot of paper in front of you. Walk around and help you guys out. And then about the last 10 minutes of class, we'll go over those solutions with you guys.
Mr. Griffin.
Yeah.